Okay, let's so we discussed wave propagation in elastic media last week and went through it and saw the equations, the partial differential equations for P wave, S wave in 1D and in 3D. We'll quickly recap what we discussed last week and start from there. So we have seen the general overview of wave propagation. We have waves all around us: water waves, roping vibration, electromagnetic waves, sound wave, or the one we are focusing, seismic waves. And we have different various forms of waves. Mechanical waves can be longitudinal waves, or we call also compressional waves. And we can have also transverse waves. And we have seen some parameters and some characteristics of waves: wavelength, period, frequency, and wave velocity, where wave velocity is just the wavelength by period, or a wavelength times frequency, the wave speed. And some characteristics of waves: we have seen reflection or refraction, which is the bending nature of waves, or wave interference. And refraction is, it's applicable to seismic in our case, but it can be for any kind of wave. And the diffraction, just a geometrical spreading of waves. This has also a big application for geotechnical engineering, but because we are talking about radiation damping, where waves scatter in all directions and get weaker. In seismic waves, we have a body wave, surface wave, and various divisions. And the body waves can be P wave, or they call it also dilatational wave or compressional wave, because the particle compress and relax along the direction of the wave propagation. S wave, in the other case, the particles move perpendicular to the main wave propagation direction. And surface waves, when we say surface, we are on the ground surface. So you can have lava wave where laterally, sideways movement of the ground surface. In the relay wave, it's like a water wave where you see the particles inside. If you take a section, it looks like they are moving in a rotating axis, and the ground surface like undulating up and down. So we discuss all these parameters. And surface waves, shear waves, can be SV or SH, depending the plane of propagation. Give me 1 second. In lava wave, like we said, it's side-to-side movement of the surface of the ground. And seismic waves, like X-rays disclosing a human body, seismic wave also, they tell us the inside information of the Earth. And if an earthquake occurs somewhere on Earth, we have regions that we call P wave shadow zone. The P wave shadow zone is an area where no P wave will be recorded. So there are certain parts of the Earth's surface that even if we have a recording station, they will not feel anything because of the bending nature of the wave and because of the interior of the Earth, especially because of this liquid outer core. It bends. A solid part, you can see anything, P wave and S wave. The P wave are those who are in the yellow. The S wave is those who are in the dark or black arrows you can see here. So before it touches the liquid, you can see both P wave and S wave. But once it touches the liquid outer core, only the P waves, the yellows, pass. The yellow. So you no more have the S wave, which is the darker color. Even the P wave, because of the bending through the liquid, it bends away, and there is a region. This gray region is a P wave shadow zone, which means you don't see any P wave. And in this entire area, you don't see any dark arrow. That's called no direct S wave, or we call it S wave shadow zone. So about half of the world, you don't see the S waves. This is the nature of seismic waves, and it has a big advantage of understanding the interior of the Earth. And the interior of the Earth, it's solid. It's discovered because of this analyzing these waves. Earlier scientists discovered on that one. You can see more detail in this link if you want to read more about it. We also looked at last week review of stress and strain relations in soil from our engineering mechanics. And using this stress strain relations, we developed a one-dimensional wave propagation. Like if you apply a compression force or a hammering on one side of a bar, then that's like a compressional wave, a dilatational wave. So the wave passes through this bar by compression and relaxation of the particles. And using this concept and considering like infinitesimal element within that bar, we developed the equation of that wave propagating through the bar. And that second order partial differential equation of that wave propagation, it tells us about the speed of the wave through that bar. In this case, the primary wave or the compressional wave or the dilatational wave, whatever you call it, the speed is the square root of the elastic modulus of that bar divided by density. As simple as that. And this is what our most interest is. And if you constrain that bar so it doesn't, strain in the lateral direction, then you can use the constraint modulus instead of the elastic modulus. And we also developed a particle velocity. When a wave travels, the particles, they have a speed. They don't travel with the wave, but they elastically go back and forth. So we developed the particle velocity can be given by the stress we applied divided by the density divided by the wave velocity. So the stress we apply can be expressed into density, wave velocity, particle velocity. And this we'll use it today around the end of the chapter when we talk about damping or the finite element modeling. This has a big application. I'll show you when you reach to it. Similar to the compressional wave, we also developed the equation for torsional waves, also called shear waves, and we arrived to similar equations for shear waves. And the shear wave velocity is the square root of g by rho. G is the shear modulus of the soil. And the solution of one-dimensional wave propagation, this is the second order partial differential equation. V can be primary wave or secondary wave or compression wave and shear wave. The solution of this equation from advanced math, it told us it has a form of this. And this is telling us at the same instant of time, you can have two waves, the incident wave and the reflected wave. So this is just the meaning of it. You can have, if you apply a seismic wave, you can have incident wave going in the same direction, a reflected wave coming back, especially if you have some interface difference, then part of the wave also gets transmitted. We'll see the application of this equation when we come to a layered soil, because in a layered soil, you'll have reflection and transmission through it, depending on the density and the wave velocity. More parameters of wave, a wave number, and a wavelength. And also similar to the 1D partial differential equations, we also looked at the three-dimensional wave propagation and arrived to the three-dimensional wave propagation equations. And they also provided the same shear wave velocity and P wave velocity for the wave. So VP is just elastic modulus by density. Now, in the case of 3D, we considered infinite space, which means constraint. We are deep inside the Earth. There is a stress on the element in all direction. So now, instead of a free bar, we are using a constraint modulus. So VP is also had this form, and finally reduced it to this finite form. And so the P wave, you can have different names for a P wave: directional wave, primary wave, P wave, or compressional wave. Similar to for the 3D primary wave, we also looked at the torsional waves and found the same similar equations for the wave velocity for the shear case. This must be an error. I'll fix it. Usually this should be an equation rather than a statement inside. Maybe copy paste error. I'll fix it and send you another slide. So summary of waves in elastic medium. These are the big takeaways. Wave velocity for VP and VS, and especially the ratio of VP and VS telling us VP is faster than VS. And the more rigid the material is, the higher the shear strength is compressional wave velocity. And shear and compressional velocity decrease as the density of the material increases. And liquids don't have shear stiffness or shear rigidity or shear modulus, so we don't have shear wave velocity in liquids. So you can go through the summary. And this is just a comparison of the VP and VS, and for different material with different Poisson ratio. And as you get close to a Poisson ratio of 0.5, you have the VP-VS ratio going much larger, which is 0.5 is like getting close to water. Soil is normally around 0.3 to 0.4 area. So I believe we were right here. We stopped here last time. So stress waves in elastic half space. Now, when we talk about infinite space, we were considering an element from inside Earth, somewhere here. So we're considering it's infinite in the other direction. But now we're going to talk elastic half space. When we say half space, we're talking below the ground surface. This is the ground, then below. So we're considering half of it. And the other half, which is above in the air, you don't have it. So that's the name, which is elastic. And when we say half space, that's what we mean. When P waves and S waves reach the Earth's surface boundaries, they transform into surface waves. So if you sit right at the focal point where the earthquake occurs, you have body waves, and they propagate in any direction. You can have these directions, and you can have right above going here. When they reach the ground surface, then they turn into surface waves. The surface waves is just Rayleigh waves or R wave and Lav waves. Usually the surface waves, they are bigger in magnitude, near to the focal point, near to the epicenter, but they disappear quickly. So if you are around the epicenter area, you'll have a significant impact from the surface waves. But they dump out quickly. They don't travel, all around the surface like this. Surface wave travels slower than body waves. We'll see this quickly. Mathematical proof how surface of Rayleigh waves and Lav waves have lower speed compared to the body waves. Surface waves are more damaging to surface structures such as buildings, as they cause to fall and rise, which is a Rayleigh wave, and also sway laterally, which is a Lav wave. They are more damaging because they deform the ground significantly, especially if you are close to the epicenter. So Rayleigh waves, we already discussed this. You can see the damages. These are computer models but it tells you, for a good understanding how the ground, undulates. This is on the ground space. We are talking about half a space. And Lamb theory of wave propagation for Rayleigh wave. This theory is, a scientist called Lord Rayleigh. He discovered the Rayleigh waves in 1985. But a detailed mathematical formulation for Rayleigh wave was discovered by Sir Horace Lamb in 1904. And this theory is what is called Lamb theory of wave propagation. That's specifically for Rayleigh waves. Now, if you have elastic half space like this, anything, you can have a foundation, then below the ground, then the Rayleigh waves are traveling around the surface or slightly in the shallow area. So what Lamb developed is an equation for Rayleigh wave, and he arrived to this equation. You can see the detail of this equation in reference to, I think that's Praja M. Dash book and section 313. So there is a detailed derivation of this equation. So he considered a plane wave an elastic half space, and he developed this. The V, the capital V you see here, is the ratio of Rayleigh wave velocity to a shear wave velocity. And alpha you see here is the ratio of shear wave velocity to P wave velocity. And this is just in the form of the material property, such as Poisson ratio. So he has this 60-degree form of variable V raised to 6 minus 8 V raised 4 minus in bracket 16 alpha square, blah, blah, all this equals to 0. And if you put different Poisson ratio, different materials are common materials from 0.25 to 0.5, 0.25 to 0.5, you can find the ratio of Rayleigh wave velocity to shear wave velocity. And for these are common materials, you can see what the ratio is. So this tells us the Rayleigh wave velocity is like 0.91, 0.93, 0.95. It's slightly above 90% of the shear wave velocity. So Rayleigh wave velocity is about 90% of the shear wave velocity. So note that Rayleigh wave velocity is about 90% of the shear wave velocity. So Rayleigh wave is slower than shear wave, but for different materials, it's about 90–95%. That's why earlier we said Rayleigh waves are slower than shear waves, but they are about 90%. You can see it in this chart. Last time we have seen this for P wave and S wave. V by Vs, this V can be, if we keep the Vs constant, and V's, it can be Vp, a primary wave, this chart, or it can be Rayleigh wave, this chart. You can see the Rayleigh wave is about close to the S wave. And as the Poisson ratio increases, you see it almost, it's getting identical. That's why it's like the 90% is Rayleigh wave is about 90% of S wave. And then we know that P wave is much larger than S wave, higher speed. And love waves, we know that what they do is, if you have structures like this in a line, same column, when love wave happens, it's side to side deformation of the ground surface. Or you will have this dislocation in the buildings. Love wave velocity depend on Earth's structure, but it's less than the S wave and slightly faster than Rayleigh wave. Hence, at recording station, love waves arrive after S waves and before R waves. R wave is Rayleigh wave. So love wave, this is very, very interesting. So for love waves to occur, you need to have certain conditions satisfied. You need to have a layered ground. If you have a homogeneous space, uniform space, whether it is a rock or soil, if it is uniform, you don't see love waves on the ground surface. Lava waves occur when you have a superficial layer very shallow, let's say the first 100 meter or the first 50 meter, when the velocity, shear wave velocity of the superficial layer is lower than the half space. Let's say this is a rock, and the top surface is, let's say, soft soil. When that happens, when the earthquake enters this area, what happens is it enters, reflects back, and there is significant reflection and refraction. Of course, part of it goes back, and surface waves created here. But between this soft layer, there will be continuous reflection back and forth. After some time away from the epicenter, what you see is just a lava wave. Because of this continuous reflection, there is a wave just propagating within that soft layer. That's what you see here. So that lava wave, it's significantly, it's usually called a trapped wave. It's a wave trapped in the softer material at the top. You see it, most of the deformation, most of the wave is within that layer, but it disappears when it goes into the half space. So for a lava wave to occur, you need to have a shallower or softer surface, and then a deeper, much deeper half space with a larger velocity. And scientists developed these equations for the deformation of the lava wave in terms of distance. The wave velocity, the displacement of lava wave is given by the displacement, or maybe I may be wrong with this one. It should be maybe velocity. This word need correction. I'll fix that one. So the velocity is described in terms of distance, horizontal distance, and depth, z, and time. So it's variation with the space and time. So you have this equation to describe the movement of the lava wave. So lava wave displacement amplitude varies sinusoidally with depth in superficial layer, which is, this is a superficial layer we are talking, and decays exponentially with depth in the underlying half space. It decays exponentially, which means it disappears after some depth. So most of the energy, 90%, 80%, it's within that soft layer. It's a trapped energy. Because of this, lava waves are often described as SH waves that are trapped in the superficial layer. We call it SH because its plane of propagation is the horizontal, and it's a trapped wave. If you have a continuous, uniform, homogeneous system, you don't get lava wave. For a lava wave, you need to have a softer superficial layer underlain by a deeper, high velocity layer, like something like a rock. The lava wave velocity is given by the solution of this. You have this equation in the form of omega. Omega is the forcing frequency of, let's say, the seismic motion. H is the depth of that layer. VS1 is the shear wave velocity within the first layer. VL is a lava wave velocity. G is the shear modulus of the second layer over the first layer, lava wave velocity, and VS2 is the shear wave velocity in the second layer. So to solve this, you need to solve it for VL. You may have to use something like MATCAP to solve this. For different values of VL or omega, you can have the VL, or you can see it in plots. If you have the first layer with VS1, which is slower than VS2, the shear wave velocity in the first layer is lower than the shear wave velocity of the second layer, because we need to have a softer layer. And for different omega forcing frequency, forcing circular frequency, if you solve this equation, you have a lava wave, which is changing from the VS2 to a VS1. So the lava wave velocity is between the two, depending on the forcing frequency from the ground motion. Waves in layered medium. Now, our soil, our geotechnical system, it's stratified. You have different layers. So that's why we see these waves in layered media. We have significant wave reflection, refraction going through another medium. To understand that, we need to see the behavior of waves, how they behave at interface, and how they move from one layer to another. That's what this section is covering, waves in layered media. Let's assume you have a bar. This is a 1D wave propagation, like a P wave. Let's say that bar has a density 1, and let's say it has a constraint modulus of 1, or this means also elastic modulus. And let's say there is a shear wave velocity of V. So if we consider this part of the bar as bar 1, and this part of the bar, let's say they have different properties, different density, different elastic modulus or constraint modulus, and different shear wave velocity. So if this happens, then you'll have wave reflection. Let's say you applied some stress right here, and you have incident stress or incident wave. This is the energy. Then at that interface, then you have a reflected wave, and part of it also gets transmitted. From the solution of the wave equation earlier, we know that the incident, this can be incident wave stress, which varies in terms of distance and time in the bar. And that was given by the initial or the amplitude of stress times this complex function. E the power of I is square root of -1, which is a complex number. In bracket omega t minus k1x. A function of t and x, k1 is a constant. This is for the incident wave. And for the transmitted wave, which is this one, which is in the same direction to the incident wave, you have the same expression, except the magnitudes change now. The transmitted stress, the amplitude, and the same function now k2, but same sign. And for the reflected stress or reflected wave, you have this expression. If R is reflected wave. Same pattern. Now it's in the opposite direction, it's plus K1. That's the difference. If you consider this wave expressions for a wave behaving at interface, and the deformation have the same pattern. The deformations of that wave, the incident wave, by the amplitude of the displacement, and similar complex pattern. For reflect wave, the amplitude by similar complex pattern. Transmitted wave, these are the same equations to the stress, except now we are talking in terms of displacement deformations. Using the stress strain and strain displacement relations from earlier section, we try to solve for the incident stress. We say the incident stress is the constraint modulus or elastic modulus times the strain, right? Now strain is rate of deformation in the x direction. So if you take the first derivative of this displacement or deformation expression, that's what you get as a strain. It varies with distance and time. And if you do first derivative of this with respect to x, then x is your variable, then minus k1 comes out. I also comes out. So what you get is minus I k1 m1 ai, and same displacement pattern here, same complex pattern. But earlier we said the incident stress is, we said sigma I, small I, times this complex pattern. So this sigma I, the amplitude, is now this portion. That's why you see it here. The amplitude portion of that complex wave is minus I k1 m1 ai. This is in terms of stress. We can do the same thing, and if you rearrange all this, the ai, the amplitude of the incident wave or the displacement, you can get it from here. The ai is sigma small I minus divided by this ik1 m1. So this is just in the form of displacement. This is in the form of stress. You can do the same algebra, same simplification for reflected wave and transmitted wave. You'll have these forms. Now, if we do, if there is a wave traveling through this bar for 1 decade, and if we consider at that interface where the two materials are differing, then there must be equilibrium. There must be displacement and stress compatibility at the interface. At the interface, let's say x is 0, displacement is 0, then the incident wave displacement or deformation plus a reflected wave, this is the one on the left side. Incident wave, reflected wave deformation should be equals to the transmitted wave deformation. So whatever deformation we have here, whatever caused by incident wave and by the reflected wave, the sum of these two should be equal to the sum of the deformation by the transmitted wave. This is what it tells you at x equals to 0. The same is true for stress compatibility. Stress caused by the incident wave plus stress caused by the reflected wave, they are in the opposite direction. They subtract, equals to the net stress by the transmitted wave. If you do that from this stress and displacement compatibility, you will arrive at equations for the stress and displacement. And the amplitude of the displacement for reflected wave, R is reflected. It can be given by in the form of the incident amplitude with some multiplier, 1 minus alpha z over 1 plus alpha z. So the derivation of this equation, you can see it in reference 1, the Kramer book, section 5.41. If you're interested in the detailed derivation. But our most interest is, okay, how much the amplitude, the displacement amplitude is amplified or de-amplified. So for the transmitted wave, you can get the same thing. If you know the incident wave, if you know what is coming, you can see how much the transmitted wave is amplified or de-amplified. If we know our wave coming from here, we can talk how much it is, the reflected wave is how much, what size it has in terms of displacement, in terms of stress also. They are the same pattern for stress too. So we can tell how much is transmitted. This alpha z is, it's called impedance ratio. Impedance ratio is the ratio of density times velocity. Density 2 of the material, this. If a wave is propagating in this direction, this is material 2. The density of material 2 times the wave velocity in material 2. In this case, we have a p wave divided by the density of material 1 by the p wave velocity of material 1. This ratio is called impedance ratio. And it tells us a lot. It has big application for geotechnical seismic engineering. So our interest is if we found the relation between incident wave and the wave passing through. If we know this amplitude, we can tell how much is passing. If we know what is coming here, we know how much is reflecting. So focus on this part. The first two slides, whatever we discussed here, I'm just trying to show you how we arrived to the impedance ratio part. But this is our focus. Knowing the impedance ratio, knowing the density of the material, knowing the velocity of the wave in that material, if we have a layered system, we can talk about what is coming, and if we know what is coming, we can predict what's going to happen when the wave passes to the next media. And this is a section of the application of what we just discussed. So impedance, knowing the impedance ratio. Impedance ratio is a very simple term. Let's see, instead of a bar, let's consider a soil layer with 2 layers. soil system with two layers. Let's say we have a rock, deep rock. Let's call it half a space. We have a density 1, V1. We're saying that a seismic wave is coming to the ground surface. And let's say our rock or the layer underneath, it has density 1 and velocity 1. Let's assume there is another surface layer, density 2, V2. This is a direct extension of our bar example in the previous section. So let's consider different cases. Now, density and shear wave velocity, we can get them from lab tests. They're easy to get. Do a lab test, get the density, and get the shear wave velocity, P wave velocity. If you know the elastic modulus, you will get, or the shear modulus, you will get the P wave and S wave. So knowing the impedance ratio is simple. But let's see the interpretation, what it means. Now let's see case 1. When the impedance ratio is the ratio of density 2 times V2 by density 1 V1, we're assuming a wave propagating upward, coming to the ground surface. When the impedance ratio is between 0 and 1, we're talking this area. I hope you can see it. When the impedance ratios, so impedance ratio, you see this table. I took this table from table 5.1 of reference 1, SL Kramer book. So I want to make sure you understand what it means. So if you have impedance ratio between 0 and 1, it can be 1/4, it can be half, it can be any number. These two are taken for example. Let's say that you have incident wave. The amplitude of the incident wave and the displacement amplitude is AI. Then a reflected wave, it's going to be for AI case, it's going to 3 AI 5 by 5, AI by 3. It decreased. The transmitted wave, what happened to the transmitted wave? One of you. 8 AI by 5, 4 AI by 3. So you see 8 by 5 is larger than 1. So the transmitted wave, it's amplified. The reflected wave, it's de-amplified. If you see it for stress, you have stress, the incident stress. For reflected gaze, minus 3 sigma I by 5. It got different polarity in different direction. And it also decreased, 3 by 5. The amplitude is decreased. It's less than 1, the ratio. The transmitted stress is also, it decreased, 2 by 5, 2 by 3. So let's see these conclusions. If you have impedance ratio of between 0 and 1, which means between 0 and 1 means this density 2 times V2 is less than density 1 V1, which means this is something like soil, softer soil, underlain by a stronger soil or rock. So we have a softer material at the top. When that happens, if a seismic comes from deep down Earth, then incident wave is approaching a softer material. That's the first conclusion. If you have impedance ratio between 0 and 1, it's clear that we are approaching a softer material, like soil. Why? Because density 2 V2 is less than density 1 V1. It must be softer. If it's a stronger, it should be greater than 1. Second, displacement amplitude of transmitted wave is amplified. The displacement amplitude of transmitted wave is amplified. Yes, it's amplified. But it's de-amplified for reflected wave. For the reflected wave, it's de-amplified. You see it here. So what it means is a wave is coming here with amplitude of AI in the rock. When it gets into the soil, it's getting amplified. AI, it can get, let's say, 8 by 5. Can get into 1.5 times AI. So this soil is amplifying it. A softer soil always amplifies seismic if it's underlain by stronger soil or rock. That's the takeaway. So soil on top of bedrock amplifies seismic motion and is bad for structures built on soft soil. If you have a softer soil underlain by a stronger soil or even rock, expect amplification. I'll give you a good example of what we saw in chapter 1. The 1985 Mexico City earthquake, where resonance occurred. I saw it there. You saw it there. When the wave passes from rock to the soft soil, it gets amplified a lot. Give me a second. I can show you that portion. I should have it somewhere. Yep, he's right here. The Mexico City earthquake. This is rock. When it gets into a softer material, the motion amplified a lot. The displacement, the acceleration, and velocity, they amplified a lot. That's what it means. So it's bad for structure. When you have a softer soil underlain by a stronger soil, and for seismic case, it's bad. Stress amplitude, in the case of stress amplitude of reflected wave is smaller than that of incident wave and is opposite in direction. For a stress case, whatever stress coming here, it gets smaller. Rock has larger stress than in the soil. An incident compression pulse will be reflected as tensile pulse and vice versa. This opposite sign is telling you if you have a compression stress coming at the boundary, it changes into a tensile. But the magnitude gets reduced in the soil layer. Now, second case. The second case is, what if you have impedance ratio larger than 1 and less than excessively large? So let's say we're talking this area. Impedance ratio greater than 1, and assume it's less than infinity, or it's not too great. What it means is you have a seismic wave coming from deep ground, and now density times V2 is larger than density of V1, which means this is the top surface has larger value than the half space. In this case, it's something like this. You have a rock at the top and underlain by a softer material. Let's say it can be soil or something softer than rock. So the top layer is now very dense or very stiff. The impedance ratio is greater than 1. What does that mean? It means incident wave is approaching stiffer material, right? This incident wave coming from here, this is the incident wave coming. This is the layer. So it's approaching a stiffer material. It must be stiffer. If the impedance ratio is larger than 1, then it's approaching a stiffer material. If it's approaching stiffer material, let's see what happened. The displacement amplitude is this area. Stress amplitude is this part. These are all they obtained from the equations we derived before. So the incident wave for displacement AI approaching from here. Now see what happens. 1/3 of AI, 3/5 of AI. This is for a reflected wave. For transmitted wave, it's 2/3 of AI and 2/5 of AI. So the conclusion is If a seismic wave is approaching a stiffer material, the wave de-amplified when it enters the top layer. The wave is not, the displacement is not being amplified. Displacement had direct relation to velocity and acceleration. So it gets de-amplified. In case of stress, what happened? The stress from the incident wave for reflected wave is de-amplified. It's 1/3 and 3/5. But for the transmitted wave, which is here, the second layer, it's amplified. 4/3, 8/5, at least for this value of impedance ratio we are considering. So stress gets amplified, but displacement, velocity, and acceleration, they are getting de-amplified. So this is the conclusion. Displacement amplitude for both transmitted and reflected waves are de-amplified. If strong materials such as rock overlay soil, there will not be seismic motion amplification, which is good for structure on the stiff material. It's common sense. If you have a stiffer material at the top, and if you want to build some structure, that's good for seismic. You don't want softer material underneath. And this is a mathematical proof. If you have a stiffer material underneath the structure, the seismic motion coming from deep ground is getting de-amplified. De-amplification is for acceleration, velocity, and displacement. But stress, it gets amplified. The stress increases within the stiffer material. Now, if stress increases, then shear strain is going to increase. So deformation within the particles within this medium is going to increase. Strain and stress. So we have to check strain and stress levels within this material. There may be failure because excessive stress. That's what we have to check. But in terms of inertial force, acceleration, displacement, or velocity, it's de-amplified. So stress amplitude of transmitted wave is larger than the incident wave. This may cause large strain issue on the stiff material, and it needs to check the strain level to avoid soil failure by large strain. But this is not a common issue. Sometimes it happens, but failure by large strain is not that common compared to amplified accelerations. Let's see case 3. Case 3 is when the impedance ratio is 0. This guy right here. If impedance ratio is 0, what does that mean? Which means density 2 times velocity 2 divided by density 1 V1 is 0. Something must be 0 here, or close to 0. It must be really, really small value of density or really low value of V. And relatively, this density 1 V1 must be really large. This is what practically it means. The incident wave, the wave coming here, is approaching free end, such as ground surface. So if you assume this is homogeneous, and when the incident wave comes, what we have as second material is really air, the atmosphere. Very low density compared to the Earth. Very low shear wave velocity, practically nothing. The waves are not going into the atmosphere. That's what it means. The incident wave is approaching free end, or it's approaching ground surface. There is no layer stratification, it's just coming to the ground. So if that's the case, the incident wave AI and the reflected wave, they will have the same amplification. But the transmitted wave, it becomes 2AI. What's the transmitted wave? The transmitted wave is the wave which is created right here. We're talking about now the surface waves. The body wave coming from deep inside, as soon as it reaches to the ground surface, it's creating those surface waves, Rayleigh wave and Law wave. And the amplitude of those waves, it's amplified. It becomes twice. If we have a shear wave, P was coming here with amplitude of AI, the reflected portion, it's AI, same. It goes here, then it comes back for reflection. That reflection have the same amplitude, but the wave that is created on the ground surface, it has 2 AI, significantly amplified. That's what we say surface waves are bad for structures. They create a very large deformation. How about for stress case? Stress case, the incident wave has sigma I, the reflected wave has just opposite polarity, which means tension will be compression, but the same value. Transmitted wave, there is no stress because it's atmosphere. There's no it's being released as a deformation. In case of stress, because it's free end, there is no stress to accumulate here. That is being released as with large displacement. So to compensate this zero stress at the ground surface, what it does is it's becoming the amplitude of the displacement is becoming twice. That's what it means. When you have impedance ratio of 0, that's the implication. Incident wave is approaching free end, such as ground surface. No stress to be transmitted, 0. Reflected stress amplitude has same amplification to incident wave, but opposite in direction, which means free end reflects compression wave as tension wave and vice versa. Displacement amplitude of transmitted wave, this guy right here. Or boundary wave such as surface wave in this case, doubles to AI to compensate 0 transmitted stress condition. But the reflected amplitude is the same. So make sure you understand these cases. These have direct application to our geotechnical engineering, wave reflection, refraction, and what happens when it goes there. We have a fourth case. How about if it's excessively large? Impedance ratio is like infinity, or we meant to be very large, which means the density to the V2 should be really large compared to this one. This is a case where incident wave is approaching fixed in boundary condition. Very large, it's fixed in. It's like we had a bar. These equations are developed for a bar. If the bar is fixed at one end, we're saying no motion at this end. That's when you get impedance ratio like infinity. The wave comes here, it doesn't go through because it's fixed end. No stress, no deformation on this side. Or no deflection. So what happens is you have a stress, you may have, because this is fixed end, you will not have any deformation. All 60 degrees of freedoms are 0. But you will have a stress accumulating on this support, on this fixed end. So a wave comes through, hitting a fixed end. So no displacement to occur at the fixed boundary, which means you can see it here. This is the case, the last case in the table. Incident displacement amplitude comes, it returns back with the same magnitude. The wave comes here and reflects back with the same amplitude, but it's opposite. But does it get transmitted? No, because this is fixed end, no motion. It's 0. How about for stress case? Sigma I, incident stress comes, and it reflects back with the same amplitude. When it gets transmitted, the stress can be transmitted to the boundary. It's not going away, but it creates a large stress in that boundary, a magnitude of 2 sigma I. Remember, when it is free end or ground surface, it was 0. When you fix it, if a wave comes, it creates a large, it doubles. So no displacement to occur at the fixed boundary, but reflected wave has same displacement amplitude but opposite in polarity. The stress amplitude of transmitted wave at the boundary in this case doubles. That's what we discussed to compensate zero transmitted displacement condition. This must be the last case, a case of where impedance ratio is 1. Impedance ratio of 1 means density times V2 is the same as density times V1, which means really the incident wave is approaching the same material. If impedance ratio is 1, which means the product of these two is the same as the product of these two, is telling us the incident wave, it's filling the same material. There is no difference really. You can have different parameters, different densities, different velocities, but as far as the product is the same, the wave, the seismic wave, feels as if it's entering the same material, as if there is no really stratification. You can have density 2 different from density 1, V2 different from V1. But if the product of density 2 V2 is the same as density 1 V1, it's like uniform material for seismic wave. Normally, we don't call it the same material. We still do stratification as a geotechnical engineer. But for a seismic wave, it feels the same. So the incident wave is approaching same material. No reflection. Even if you have different densities, different velocities, as far as the product is the same, no reflection. It just go through. It enters as if there is no boundary because impedance ratio is 1. This is that case. Transmitted wave has same displacement. Incident wave, displacement amplitude AI. Reflected wave, there is no reflection. You see it? In both stress and displacement, it's 0 because it feels the same. For transmitted, well, if there is no material change, then AI would be AI. Same displacement amplitude, same stress amplitude. So this is a unique concept. Even if geotechnically we say we have 2 layers, if we have 2 different densities and 2 different shear wave or P wave velocities, for a seismic wave, if impedance ratio is 1, it feels the same. That's the conclusion. Transmitted wave has same displacement and stress amplitude and polarity. This concept is used to represent infinite rod or half space with dashpot model. Okay. This, we will see it in the next slide. It has application. If we think these 2 materials the same, then we can take advantage of that property if the impedance ratio is 1. Let's see this. Now, if you have a bar, if you have a wave coming through it, and we discuss if you have interface, you can have incident wave, reflected wave, and transmitted wave. And if you have a stress here, we know that stress wave, we can calculate the force on it. Force is stress times area. If you know the cross-section area of that bar times the stress acting on it, that's a force. But stress caused by a wave propagating through here, we derived it earlier. That stress can be given by, remember the particle velocity we talked? Over there, we derived the density times the wave velocity. Vm is now wave velocity in the material. It can be Vp, Vs. Times the particle velocity is a stress. We derived that somewhere in this chapter, I believe. Let me see, we should have it. Yeah. If you go to the section on slide 26, where we discuss particle velocity, you'll have that. That's the reason we derived it, because we need it. Stress, the wave creating a stress is given by the density of the material, the wave velocity times particle velocity. If you replace that, then Now we have density VM. VM is VP or VS, it doesn't matter. Area, the cross-sectional area of the bar times particle wave velocity. And if you represent this C, now the force is, if you see it, the force is with getting it as C and support proportion of particle velocity. This is, if you remember it, in the general equation of motion, this is the damping force. Now, you can call it C is now density times wave velocity times area. Now, the last case we have seen is, okay, if we are entering to the same material, we say that there is no really practically any difference, which means let's assume these two materials are the same. These two materials are the same. The density times V material, the density times V material. So which means it's like having a very long rod, infinite distance. So we can cut it somewhere and really represent this portion by the damping force we just developed. What it means is you have a wave propagating in one direction. Mathematically, if you represent a damping model where it completely absorbs that wave, then we don't need really to have a long rod. We can have a short rod and represented the remaining portion of that rod represented by this damping model. This is for the wave part, wave propagation. So the direct application of this is something like this. Let's say you are modeling using Flux 3D, a dam model or a building. Let's say you're modeling a building model. You have your nearby geotechnical soil layers modeled, but you can go deep in the ground. After this, let's say it's uniform material, it's rock. The density is the same, wave velocity is the same. But in our finite element or finite difference model, we don't need to include too much length here. We don't need it. We can cut the model size by representing the remaining portion by a damping model. We can get the damping density times. Give me 1 second. The kids are disturbing a little bit. Okay, they are keeping quiet. Let's continue. So that's the application. So this axial force is identical if the semi-infinite rod replaced with a dashpot of coefficient is much. So we can really represent a portion of that rod with a damper to absorb the wave. So which means we can really have a small model and the wave, it's passing through. It's not returning. It's feeling the same as if it's the same material. And we absorb it with a damper. This concept has a wide application SSI, which is soil structure interaction analysis and ground response analysis. And let's see what it means. This is familiar to you now. Let's have a model of a dam. And let's see that we are including some portion of the ground with the dam model. Something like you can model this in Plaxis 3D, Flux 3D, or 2D, or UDEC, 3D, Shake, whatever software you're using. When you do that, if it's a static model, you can do the spin supporters. These are applied for stability. And let's say there is no dynamic load. So all your load is this gravity load and a water load, lateral load acting on the dam. Then stress is here. So if you contain, let's say about, I think they call 7 times to 10 times of the width of the dam. If you include that, the displacement around is probably negligible. You can determine the boundary size, the length of your model by doing some sensitivity, by checking stresses and displacements around the boundary. When they get almost negligible, that's your boundary. Now, dam model with pin support boundary condition. This is good for static analysis. It's perfect. That's okay. Sometimes you can even fix it here. but it's bad for dynamic analysis. Why? It's because the waves entering the model reflect back. Now, if you have a wave entering here for a seismic kit, that wave hits the surface, do the shaking or whatever it does, it reflects back, right? Some of the wave. When it reflects back, this pin support or pin fixer support is not absorbing it. Whatever reflection here, we want it to come out. We don't want it to reflect back. So if you do a dynamic analysis, a seismic analysis only with pin supporters, what happens is you will have a significant back and forth reflection of wave. A significant energy. It's like another earthquake entering. So you have multiple, you'll have model instability issue. A significant energy you're introducing compared to what's in realistic case. So this is good for static analysis, but it's not good for seismic analysis. For seismic, now what we have to do, see the second model. You can have the same thing, the pin supporters or fixer supports. There are different boundary conditions depending on what software you're using. Those supports are used for model stability. But in addition to that model stability, you need to have dampers. You need to include damping. Why that damping is used? Because whatever energy is coming, entering the model, we want it to come out. It should be absorbed horizontally in all directions. We don't want it to reflect back and introduce another energy. So when you do seismic analysis, dynamic analysis, this is your model. You should have dampers at the end. What these dampers are, why we using this damper? These dampers are also, remember the long bar equation. We can go our model to a deep inside the earth. But for finite element, finite difference analysis, if you have a large model, you will have a solution error. It takes forever to solve it. But you can cut it down. You can cut it, represent the remaining homogeneous portion just with a damper. All we need is the energy to come out. So dam model with dashpot boundary condition is good for dynamic analysis. Seismic waves entering the model leave the model by being absorbed by the dashpot and will not have any multiple reflection inside model. For model stability, base can have a spring or fixed boundary. Depending on your model size, you can have spring supporters, or you can have pin supporters, fixed boundaries, anything for model stability. But if you're doing dynamic analysis, make sure you have these dampers so they absorb the energy trying to come out. So if you get a chance in the future to do this dynamic analysis, you will see this. You will see dampers, and that's the reason behind. Inclined waves, section 3.6. Waves are not always vertical or horizontal. They can come inclined direction, depending on the depth of, where the focus point for the earthquake is. If you have inclined wave, a P wave coming at an incline, it can create SV wave and P wave at interface between two materials. If you have a layered system, which means different impedance ratio, or you can have a reflected S wave and P wave. If you have SV wave, it's a shear wave propagating in the vertical direction. It can create a P wave, reflects back, or it can be SV wave at interface layer. Or it can create reflected, refracted P. Refracted SV and refracted P. If you have SH wave, you can create only SH wave, reflected and refracted. You can see figure 5.17 in reference 1 for this. Now, inclined waves, the reason we looked at inclined wave, it doesn't matter whatever. It can be P wave, SV, SH, shear wave, whatever it is. Now, let's see one very important characteristic of inclined wave. If the waves come from deep underground, And commonly what we have is the shear wave velocity at the top layer, they are smaller than the layers below, smaller than the layers below. You see this sample example. In most common cases, there are exceptions where you don't have this. You may have a layer, very soft layer trapped inside, it can be very low. But commonly, most places we have shear wave velocity increasing downward, P wave velocity increasing downward, like a stiff rock overlain by a softer rock, then a stronger swell, then a softer swell, like that. Remember what we studied for when wave refract, when entering to another layer. Waves bend, right? Let's say this shear wave velocity is smaller than this one. So what we said is, if a wave, like a light wave, if a wave enters to a medium with a smaller wave velocity, the wave bends toward the normal. So this theta is larger than this one right here. If I have a continuously lower shear velocity layers, then the wave is continuously bending as it enters to the new layers. So normally what happens is when that wave arrives to near to the ground surface, it's like vertical. That's the main reason you see in models, we see vertically propagating shear waves. If you have a model like this, of course, we have horizontally propagating also from the surface waves. But those body waves coming from deep underneath, they tend to be vertical by the time they arrive to the ground surface or nearby. So in software applications, you will usually see that they apply vertically propagating waves. Why? Because of successive refraction, successive bending, the wave tends to be vertical by the time it arrives to the ground surface. You can go through this right up. So that's a common way of SSI, soil structure modeling concept. So we are slowly getting into the practice, the application of this wave theory to our geotechnical analysis, especially in software modeling. 3.7, section 3.7, attenuation of stress waves or damping. Now we know that if an earthquake occurs at some point and goes to some point, or let's say our interest is around here, it's passing through different materials. The energy is propagating. Most of the energy, it can be transferred. There is damping. There is attenuation. When we say attenuation, it's the decrease in size, a decrease in energy. It's losing some portion of the energy. When you specifically consider it for soil, we can say it is a material damping. Because we have particulate materials, they rearrange themselves. When the stress comes, they rearrange, elastically deform, friction happens, and all that cause damping. So we can have two kinds of damping. We can have material damping, or we call it also hysteretic damping. We can estimate this from lab. And it's also called viscous damping. It's the dissipation of energy by a slipping or rearranging of soil particles due to cyclic loading. The loading is from seismic in this case. The damping ratio can be determined from lab as 1/4 pi delta W. Delta W is the dissipation. If you do one cycle, the energy dissipated in one cycle divided by the peak energy. If you have like a stress strain plot, you can find the maximum energy, the peak energy or the dissipated energy. It can be estimated in lab. We'll see this in chapter 5 or chapter 6, I believe. This is one way we can find the damping ratio of materials, different soil materials. If you do this, this is the damping ratio. We can estimate this. Material damping can be estimated in a lab. The other damping is radiation damping. Radiation damping is geometrical spreading. When a wave enters from a small area, spreads into a larger area, the intensity decreases. Wave diffraction, we have seen that in the first chapter. When a wave enters into a larger area, it spreads out, and the intensity also decreases. So whatever stress you have initially, if you measure it at another distance, you have rate of change. Usually it decreases. So there is a decrease in the wave energy because of spreading to a larger area. For geotechnical engineering, we call that radiation damping, geometrical damping. This is the same damping Alex asked me last time. How we, he doesn't see, most of the time you don't see this being included in finite element models. The reason is, if you already have a model included, it means a wave entering here, it can be spread out. It goes out in all directions. So you already have it. A wave entering is being spread out. When it reflects back from the ground surface, it's being spread out. Because of that spreading, indirectly, you included radiation damping by creating a 3D model. By creating a larger area over here, you are actually introducing a way for the wave to get weaker because it's spread out in a larger area. A few models like this, if you have only spring and damper, you don't have it because you didn't, provide larger area for the wave to disappear. In that case, you can do some approximation to include. But normally, you don't see radiation damping being included, partly because it's also like conservative analysis not to include it. If you don't include radiation damping, your model will show larger energy, larger displacement. It's not significantly large, but slightly larger values, which is a conservative design. Because of that, you may not see it, but if you're trying to be more accurate, you can see some literatures, how much you can approximate it. Material damping, maybe you can increase it by 5%, 10%, like that. But radiation damping, the concept is like that. A wave gets weaker because of particles rearranging themselves or spreading into a larger area. That's the conclusion of this chapter. So the main references for this chapter is the first two references. Reference 1, S.L. Kramer, chapter 5, and reference to the Braja M. Das book by chapter 3. And you have homework due 2 weeks from now from reference 1. You can solve problem numbers 5.1 to 5.4 and homework problem 5.9. That concludes this chapter. And after the break, we will start chapter 4.